All right, on to chapter 3. We're finally kind of getting into some computations here, but 3.1 is the measures of central tendency. It's basically what it's talking about. It's going to measure the center. Well, we're going to talk about the mean, which is the average, median, which is the middle, and the mode that happens the most. And we're also going to kind of interpret and explain what each of those kind of numbers kind of tells you. Measurements of central tendency, again, kind of use the term average to indicate one of the measures that's the center of the population. But there are some times where these averages are actually better if it's the mode, better if it's the median, better if it's the mean. We'll talk about the pros and cons of each of those. First off, the mode. The mode of any set of data is the number that occurs the most. So here are 16 students that are asked how many college math classes they've completed. Looking through, you've got a bunch of ones here, so the mode is 1. Okay. When you're calculating the mode, it's okay to have either no mode, so no number repeats itself at all, or it's possible to have 2 or more modes. So you got maybe not only the class of 1 class, but maybe the 2's tied it. So 1 and 2 would both be the modes. This would be very good. I think of it in terms of like if you're going over to maybe work at a job that's hiring a lot of new like college students or high school students to go work, and a lot of them are going to be working minimum wage. So the best representation of the people who work there would be the mode because that's the most people making that type of money. Median is the middle number of the data. Equal number of data above and below the median. Uses the position of the data values rather than the actual value, and is slightly only affected by an extreme data value, or in other words, an outlier. So median, it doesn't matter if you have one really, really small number, one really, really big number. It shouldn't affect the middle number that you're looking at. Find the median of a raw set of data. Order the data from the smallest to largest. There are ways to do this on your graphing calculator. We can talk about in class and work through with that. If there is an odd number of values, so let's say there's 7 numbers, the median is going to be the exact middle number. When there's an even number of data, say like there's 16 numbers, now you're going to have to go and you're going to have to find the sum of the 2 middle numbers and divide by 2. Or in other words, you're going to find the average of those 2 middle numbers. It might turn out sometimes that your median is not one of the numbers in your set of numbers. Okay, to find the position, here's a little trick you could work with. Let's say there's 7 numbers. So 7 plus 1 is 8. 8 divided by 2. The 4th number is your median. Okay. So there's 7 cans of soda that are removed from packaging plant and contents are measured. They're already put into order. So 11.8 is the smallest, 12.3 is the biggest. You could use what we did before with the 7 plus 1 over 2. So the 4th number would be your median. Or I like this trick that somebody back in my Algebra 1 pre-algebra days taught me, just to check off the 1 above, 1 below until you finally get to the middle. So that's if you got 7, which is an odd number. If it's up to 8, okay, now what's going to happen is you're going to work your way through and you're going to end up having no exact number in the middle. So you take the average of the 2 middles, add them up, divide by 2, and the median is 16.5. Now this is what I was talking a couple slides prior. 16.15 isn't a number that's in this data set, but that's fine. That's still going to be the median of those 8 things. Mean is the mean is used as all the data values to calculate the measure of the central tendency. Mean is very affected by the extreme value. So now if you have one big number, it can really throw off your average. Now I kind of get into some notation, symbol-wise. If you're ever dealing with a sample mean, it's going to be an X with a bar over the top of it, so X bar. If it's the population mean, it's a U with kind of two tails in both directions. It's the Greek letter mu, or M. Like, for example, if we got a mean and it came from the entire Cheyenne High School, and that's our population, we'd use mu. If we maybe grabbed a sample from, I don't know, maybe all the Algebra 2 classes in Cheyenne High School, that would be your X bar. They're both calculated the same way. It's just a matter of notation and reading information correctly. Because what you'll do, you'll get the formula sheet given to you, or it's in the back binding of the books, all the formulas that you'll ever come across that you'll ever need. You'll see this symbol that looks like a capital E. It's sigma. And with the Greek letter sigma, and that's capital sigma, not the lowercase sigma, is to sum up the following sets of data. If the data represents the entire population, then you might see a capital N. If the data represents a sample, you're going to see a lowercase n. So this would be saying for sample mean, okay, add up all of the X values that you're given and then divide by the number of data. Well, this means the same thing and this means the same thing. It's kind of semantics right now. It'll make a lot more sense when we're talking about using this sample mean as a good estimate for the population mean. So you take your 7 light bulbs to measure how long they last, 1 through 237. They do not need to be in numeric order, but to get this value of 1,221, you're just going to take these 7 values and add them up. That's what this means. Take the sum of all the X values. And since there were 7 of them, n is equal to 7, so 1,221 divided by 7, you got an average of 174.43. Now, if I'm looking at these numbers, there's a number that doesn't belong in my original set of data. That number 1 seems way smaller than everything else. So with that 1 in there, it's 174. The other 6 values are bigger than 174. That number 1 might be an outlier. Okay, so there's a way to kind of help out with that. It's called a trimmed mean. Okay, so we're going to trim the values and create a mean. Resistance measures of a central tendency. A resistance measure is an extreme value, high or low, that affects your mean. So basically what we just talked about with those, that one value, that 1 at the very beginning, took that light bulb average and knocked it down to 174 approximately. So here's how you would work a trimmed mean. A measure of center that is more resistant than the mean but is still sensitive to subject to data values. It's basically this. You're going to trim, so you're going to take off. You're going to order the data, make sure it's from the smallest to largest. I know I said for regular mean it didn't matter, but for trimmed mean it does. Somewhere along the lines, it's going to say, let's calculate a 5% trim mean, or let's calculate out a 10% trim mean. Those are the common ones. And then we're going to simply calculate the mean again. This doesn't quite make sense. We'll talk about an example here in a little bit. Here's some numbers. Okay, I believe, yes, there are 20 numbers in here, 15 all the way to 100. It's asking for a 5% trimmed mean. So 5% of 20, so 0.05 times 20 is 1. That 1 means that you're going to trim off the lowest, but you can't discriminate on the low numbers. You also have to take away from the top, which means that now we're left with 18. So now our trim mean for these values would work out to be 72.78, whereas the actual trim or mean with all 20 values put together would be 71.25. Here, make sure you divide it by 20. This guy, make sure you divide it by 18 because we took out the lowest number and the highest number. And to me, that 15 is probably the outlier, okay, or the resistance measure that's changing what your average or true average should be. Okay. Another one, you guys should really be familiar with this. It's a weighted mean. Your semester grades are weighted mean. By weighted mean, I'm talking about the fact that your quarter one score is weighted at 40%. Your quarter two score is weighted at 30%. Your exam score is weighted at 20%. You go through, you multiply each of these scores by those weights, and you've got your weighted average. Okay? So be careful. It says sum right here, but it's telling you to multiply X and W together. Do the multiplication first, and then go back and add up the sums. Your weight, most likely, in decimal form, that sum of W works out to be 1. If it's a percent, it's going to be 100%. So here's an example again. You go to a pageant, the interview is worth 30%. Okay, so that would be one of your weights. The appearance is worth 70%. That would be a second weight. Make sure you change your weights to decimals, so 0.3 and 0.7. Find the weighted average for a contestant whose interview score is 90 and the appearance score is 80. So we'll take the score of 90, multiply by its weight. We'll take the score of 80 and multiply it by its weight, and then add together. So 27, 56, that all together gets you 83. The two weights combined gives you 1, so you're basically divided by 1. So your weighted average would be 83. Okay, again, here's some problems. They're all odds. Work on a couple, bring some to class. We can go through a bunch of them. Weighted mean and trim mean, I think, are the big ones because those are something that's not quite as familiar to us. So don't let the Greek stuff get in the way of it for a little bit. You'll get more comfortable with it, and you'll see more Greek letters as we go too.